Hello and welcome back to the second podcast to go along with Chapter 4. So this part we're going to be taking a look at predicting products of chemical reactions and what are some of the characteristics of different chemical reactions. If you remember your patterns from previous chemistry classes, that's going to take you pretty far in helping you figure out what the products are going to be. So things like double displacement, single displacement, combustion, synthesis, decomposition. Use those as kind of a starting point. But now we're going to delve a little deeper into what is actually going on with those reactions. So the first one we want to talk about are called precipitation reactions. Precipitation reactions are when two solutions are mixed and you form a precipitate. In other words, an insoluble solid. So you're going to make something solid. You're going to make some floaties, some chunkies, and it's going to settle to the bottom of the solution. So it might be a suspension for a little bit, but eventually those two products will react to create what we call a precipitate. So it comes out of the solution. These are your double displacement reactions, so use that as kind of your starting point for this stuff. Now, how will you know what creates a precipitate and what doesn't? Well, here's where you guys got to do some memorization. You got to know these solubility rules. Now, while some textbooks say that this isn't specifically addressed in, or that you don't have to memorize them for the AP test, but yet the AP test does ask you to predict products and understand these reactions. So it's just going to save you a whole lot of heartache. Know the solubility rules. So here they are. Nitrate salts are soluble. So anything ending in a nitrate. So that would be something like sodium nitrate. Anything ending with a nitrate is going to be soluble, meaning it's going to be an electrolyte. It's going to dissociate when you put it in water. Alkali metals, so that's your very first column on the periodic table. Lithium, sodium, potassium, and ammonium salts are all soluble. The halogens, chlorine, bromine, iodine salts are soluble, unless you put it with silver, lead, or mercury. So for instance, silver chloride is insoluble, that's going to be a salt, but sodium chloride is soluble, that's going to be aqueous. Sulfate salts are soluble, unless, of course, it's with barium, strontium, lead, mercury, calcium. That's supposed to be a comma right there. Those are exceptions to the sulfate rule. Hydroxides are insoluble, except for those containing cations in rule number 2. This is rule number 2 right here. So things like sodium hydroxide, potassium hydroxide are soluble. Barium hydroxide is soluble, sodium hydroxide is soluble, but everything else is going to be insoluble. Sulfides, carbonates, chromates, and phosphates are also insoluble, except for those exceptions containing cations in rule number 2. Again, guys, just memorize these, okay? It's going to be super, super helpful, and you'll thank me later when the AP test rolls around, so just memorize these. Alright, so now that we can figure out what the precipitates are going to be, we're going to work on what we call writing a net-ionic equation. So previous chemistry classes, you wrote these things. You wrote formula equations or molecular equations, where you saw all the species that were there in the beaker, where you saw every cation, every anion, states of matter, and all those kinds of things. But so it's the complete formula. And of course it's balanced. From here on out, we're balancing everything. To get from the formula equation to what we call the net-ionic equation, first we start out with a complete ionic equation. Anything that is a strong electrolyte, so in other words, anything that is listed as aqueous, you're going to ionize. You split it up into its ions, into its cations and its anions. Anything that is solid, or liquid, or gas, you're going to leave as one compound. Don't ionize those. The only thing you're going to ionize are the aqueous solutions, so anything that's a strong electrolyte. Your next step to write the net-ionic equation is to eliminate your spectator ions. So spectator ions are things, they are in the beaker, they're there, but they are not part of the overall reaction. They're spectators. They're just hanging out, chilling in the beaker. So we don't really consider that. We don't want to consider those when we write a net-ionic equation. So you eliminate those spectator ions. See how on both sides of the equation you've got two nitrates, so they're going to be, the spectator ions are the things that are the same on both sides. So two nitrates, that is a spectator ion. Two sodiums, those are spectator ions. And if you see what's left, it leaves you with this particular net-ionic equation. cadmium ions react with sulfur ions to create cadmium sulfate. So let's try another example. If I take aluminum nitrate, I'm just going to rewrite this so I have a little bit more room to work here. That's a 3. If I react aluminum nitrate with barium hydroxide, and I want to write a net ionic equation for this, the first thing I have to do is predict the products. So this looks like a nice double displacement reaction. So do that. Switch up your cations, your anions. So it's going to create aluminum hydroxide, AlOH3, and barium nitrate. Okay. Next step I want to do is I need to balance this thing. So let's see. I'm going to need 2 aluminums, 3 bariums, 2 aluminums, 3 bariums. So now it's balanced. Yeah, start by balancing your formula equations. Next step, you're going to write out your ionic equation, the complete ionic equation. So ionize everything that is a strong electrolyte. Keep the coefficients. Okay, so I have nitrate ions. I have 3 nitrate ions within the aluminum nitrate, but then there's also 2 of them, so that gives me 6 nitrates. 3 bariums, 3 barium ions, 6 hydroxides, yields 2 aluminum hydroxide. Now I'm not going to ionize this because it's a solid. And then I'm going to ionize my other spectator here. Okay, so let me finish writing this and then I'm going to back up because I realize I just missed a very important step. And that would be, once I got my products, how do I know what's what? My solubility rules tell me that aluminum hydroxide is the solid. And the solubility rules also tell me that all nitrates are soluble, so that's what tells me that barium nitrate is a strong electrolyte. That's a 6 right there, so I have 6 nitrates. Okay, so sorry, forgot that little step, but that's the thing that tells you what's going to be a precipitate and what's not. So now I'm going to eliminate my spectator ions. So just so you guys can see it, I'm going to switch colors here. I'm going to look for the things that are the same on the left and on the right, in the product side and the reactant side. And if you notice, I got 6 nitrates here, 6 nitrates there. That's a spectator ion. Nitrate is a spectator ion in this case. I got 3 barium ions here, I got 3 barium ions here. That is also a spectator ion, so I'm going to eliminate that. Which leaves me with my final net ionic equation to look like this. 2 aluminum ions reacts with 6 hydroxide ions to form 2 moles of aluminum hydroxide. And there you go. Okay, so now from here, let's do a little bit of review of stoichiometry, some precipitation reaction stoichiometry. And we will be writing net ionic equations here, so you see more practice with that. Okay, this is out of your textbook. It's a nice flow chart of the process that you do to kind of go through stoichiometry and review. So let's look at this example. We've got 10 milliliters of 25 molar barium chloride. Remember that molarity is moles divided by liters. It's going to be important there. Is reacted with 10 milliliters of 0.35 sodium sulfate. First thing that you always want to do with these equations is we're going to write out our balanced reaction. Okay, so I'm going to take barium chloride, react it with sodium sulfate to produce barium sulfate and sodium chloride. And let's go through and balance that. So I need 2 NaCls. And now we're good. Now my solubility rules are going to tell me what's a solid, what's a precipitate, and what's aqueous. The title of the chapter is Aqueous Solution, so your reactants are going to be aqueous unless otherwise indicated. According to my solubility rules, sulfates are insoluble when you mix them with a group 2 alkaline earth metal. And these will always be aqueous. So anything with a group 1 and chlorine, these are definitely going to be aqueous. So that's my precipitate. So if I wanted to write this as a net ionic equation, let's just go ahead and do that. Let's practice that a little bit. I'm going to do barium ions, chlorine ions, and there's 2 of them, sodium ions, oops, there's 2 of those, sulfate ions, barium sulfate, I'm going to leave that as a solid, 2 sodiums, and 2 chlorines. Okay, so hopefully now you can figure out what your spectator ions are. We will ask you questions looking at a reaction. What are the spectator ions? And this is the process that you're going to use. Ionize everything, and whatever is the same on the reactant side and the product side is going to be your spectator ions. So in this case, chlorine and sodium are my spectator ions. So down here, I'm going to just rewrite my equation, because then I'm going to use this to solve the next part of the problem. Okay, so I've got, so I've got barium sulfate. Okay, how many grams of precipitate will form? Use a BCA table. Now, in the previous chapters, you guys used dimensional analysis, and that is a great tool. It is a great process if you get stuck, but I want to show you guys a little shortcut, and I would encourage you to try it this time around, because it's going to help you as we move into other units. A BCA table stands for before, change, and after. And what it's going to kind of help you see is think a little less algorithmically, just kind of plugging and chugging in dimensional analysis, to start really putting your head in the beaker and think about what all is going on with this particular reaction. And once you kind of set it up and you feel a little bit more comfortable with it, you can answer all kinds of different questions if you just set it up like this at first. Okay, so how many grams of precipitate will form? Well, if you think about the information we have, we've got milliliters, molarity, and with dimensional analysis, first thing you guys had to do was figure out moles, so that's what I'm going to do. I'm going to figure out how many moles of barium I have, and in this case, it's the barium ion, but barium chloride is a strong electrolyte. So when I have a molarity of this, that's going to give me my concentrations of barium ions and chlorine ions. So just kind of keep that in mind. Your molarity is going to give you your concentrations of ions. If you're not sure where I got this number, 0.0025, just remember this bad boy right there. Very important. Sulfates. I'm going to do the same thing with my sodium sulfate and figure out my concentration of sulfate ions. So 0.35, or not concentration, but my moles. Okay, so I got to get my moles. Now let's think about what happened. Do I have an initial concentration of BaSO4? Is there any to begin with? No, that's the before piece, the B. Nope, so there's a big old 0. Now comes the next step, change. What I want to look at is how are these going to change? How are these concentrations going to change? This is moles. And how is this concentration going to change? Now again, previously we've done this using dimensional analysis, but I just want you to take a moment and think about it and think what's really happening. With our previous types of problems in the first 3 chapters, we had to figure out what the limiting reactant is. When you set up a BCA table, it's really easy and quick to see what your limiting reactant is going to be. This is a 1-to-1 ratio of bariums and sulfates, right? But I do not have equimolar solutions. I've got 0.0025 moles of barium, 0.0035 moles of sulfate. So one of these two things is going to run out first, and hopefully you see that the thing that's going to run out first is the barium. That's going to completely get used up because it's what I have the least of. Since it's a 1-to-1 ratio, this is also going to change by that exact same amount. So now you see what you have left over. Since this is a 1-to-1-to-1 ratio, this is going to go up by that exact same amount. Okay? This goes down. That's the only way these two can change. Your reactants are going to decrease, and your product side is going to increase. That's the only way it can go. What we're looking at here in this change is what is happening to the concentrations once the reaction starts to progress, once it starts to take place. Now if you think about what we have here, we have now figured out what is the limiting reactant, what's in excess, and how much product we've created just by setting up this little BCA table. I know that this was my limiting reactant, the barium. I know that this is my product, and I know that the sulfate is going to be in excess. So when the question now says, how many grams of precipitate will form, I don't have to do 2 separate calculations to figure out what the limiting reactant is. I already know that the barium is going to be my limiting reactant, and I now know how many moles of stuff I'm going to create. So now I can just take my moles of the barium sulfate and convert it to grams. Barium sulfate, and I'm just going to convert that to grams. So molar mass, barium sulfate, 233.39 grams, 1 mole, 0.0583 grams of BaSO4. Okay? In terms of sig figs, what do we need here? Well, we've got 2 sig figs in my volume, 2 sig figs in my volume. I'm not going to really count that as much, so I'm going to stick with my 3 sig figs for the barium sulfate. Now the next part of the question says, what are the concentrations of all the ions present? If we bounce back and take a look at our table, this is a really easy thing to tackle now, because we know everything in moles. The only thing that you need to remember is that concentration is molarity, moles per liter. Okay, so we're going to have to put things back into molarity. Right now we've just used moles. Anytime you set up a BCA table, guys, put everything in moles. Okay, you got to get everything in the same unit. You can't leave it in molarity, you got to leave it in moles, and then you can convert it back into molarity later. So make sure that when you're filling out your BCA table that you put everything in moles. Alright, so now the next part of the problem says, what are the concentrations of all the ions present? You've already kind of got this worked out. So what are my ions? I've got sodium ions. That was the spectator. So we kind of saw that already. Chlorine ions, spectator, but they're still there. They're still in the beaker. Barium ions, and sulfate ions. So that's the first thing I'm going to do. I'm going to list what are all the various ions in my reaction here. So even though we eliminated the sodium and the chlorine up here as being spectator ions, I eliminated it from my net-ionic reaction. If I'm asked to figure out concentrations of stuff, I still have to remember they're in the beaker, they just didn't do anything. So I have to appreciate that fact. Okay, so let's think about our concentration of sodium ions. Well, whatever I started with is whatever I ended with. So whatever my molarity is of the sodium sulfate, those sodium ions, because remember the sodium sulfate splits up into sodium and sulfate ions. If I know my molarities of that, which I do, because it's right there, and I know my moles of that, I can then figure out my concentration of ions. So my initial concentration of the sodium ions, I figured out that I had 0.035 moles. And if you go back and you look at your balanced equation, you have 2 of them. There's 2 Na here, there's 2 Na over there. Okay, so I got to multiply that by 2. So now I know how many moles of sodium I have, 0.007 moles. To figure out concentration, concentration is moles per liter, so I'm going to do 0.007 moles divided by, now my volume. Well, I mixed 10 milliliters of this with 10 milliliters of that. If you add 10 milliliters with 10 milliliters, volumes are additive. So that's going to give me 20 milliliters. In other words, 0.02 liters. So in the beaker, I have a concentration of 0.35 moles per liter of sodium ions. Let's do the same thing with the chlorine ions. From my BCA table, I know how many moles of chlorine ions I have. Why is that? Because of the barium chloride right here. Barium split up into barium and chlorine. So the concentration of barium ions is the same as my concentration of chlorine ions. Except for here, we also have 2. So there's 2 Cl right there. So I've got 2 moles of chlorine ions. So it's not just 0.025, it's 0.0025 times 2. So that's going to give me 0.005 moles. And then same thing, I'm going to convert that back into molarity. 10 milliliters plus 10 milliliters is 20 milliliters, so that's 0.202 liters. So my concentration of chlorine ions is 0.25 moles per liter. Now the barium ions, what is my concentration of barium ions? Well, here we see that it's the limiting reactant. So whatever I started with, we completely used up. So in other words, I got nothing. There is no barium left over. Sulfate. Sulfate is my excess, and here's where this little table is really, really helpful. So if you notice, what's left over is this 0.001 moles. So I already know how much I have in excess, 0.001 moles. It's still 20 milliliters of stuff. 0.001, yeah, make sure I wrote that right. My concentration of sulfate ions that I have in excess is 0.050 moles. Alright, so that's a new concept. I get it. So let's practice it again. BCA tables are a different way of looking at it. Let's do another one with sodium phosphate and copper 2 chloride. So again, our first step that we always want to do is write out our balanced molecular equation. So I'm going to take sodium phosphate Mix that with copper chloride. Okay, these are aqueous because it says that we're mixing solutions and I know molarities. Double displacement reaction, so cations and anions are going to switch. So I'm going to create copper phosphate and sodium chloride. Okay, next step that you want to do is go through and balance that. So let's balance this. And, okay, those are aqueous. I'm going to use my solubility rules now to figure out what these two things look like. Sodium chloride is always going to be aqueous because of the first couple rules of your solubility list. Copper phosphate, this is my solid because phosphates are generally insoluble. Now let's think about what this is going to look like as a net ionic equation. We're going to ionize everything and split it up that way. And that basically leads us with copper ions. I'm just going to jump ahead here, but we can go over it more in class if you need. With phosphate ions, and it will create copper phosphate. Let's see, I need a 3 there and I need a 2 there. Okay, so now we're balanced. Now let's figure out our grams of precipitate using a BCA table. Now, as I said, dimensional analysis gets you the same answer, but it takes a little bit more time. And I want you guys to practice this technique because it will help you in other chapters, but also start to think about things a little bit more like what's actually going on with the reaction. Okay, how many grams of precipitate are going to form? From my problem, I see molarities and volumes, molarities and volumes. Remember that molarity is moles per liter. And what I want to put in my BCA table are moles. So I need to figure out how many moles of each substance I'm going to use. So this is the copper, that's the copper chloride. So I know I've got 0.005 moles of copper. The phosphate comes from the sodium phosphate. So I've got 0.005 moles of that stuff. So I have the same number of moles of both things. How much copper phosphate do I have at the beginning? Well, nothing, because the reaction hasn't taken place yet. Change. All right, now let's think about one of these two things is going to be my limiting reactant. Which one is it? So now here's where you want to look at the stoichiometry. Yes, they're equal moles. Our previous example, they were different numbers of moles, but it was a 1-to-1 ratio. Here's we've got equal moles, but I've got a 3-to-2 ratio. So if you think about this, your sodium phosphate, if we divide that in half, is going to give us what is that, 0.0025 moles. But this one is by a factor of 3. So it's going to take 2/3 of the one to equal the other one. So this is what ends up being not being in excess. This is my limiting reactant. So this is going to be completely used up. If that just completely blew your mind, let's just think about it in terms of dimensional analysis. Okay, I'm just going to kind of prove it to you down here so you can see it with the dimensional analysis. If I've got, let's just do our little sodium phosphate, and I want to figure out how many moles of my copper phosphate I'm going to create, given that I already have moles. Between my sodium phosphate and my copper phosphate, it's 2-to-1. If I use my copper chloride, and my copper phosphate, PO4, that is a 3-to-1 value. Okay, so hopefully you can kind of see, just by looking at that, why the copper chloride is going to be my limiting reactant, because it's going to take 2 moles of this and 3 moles of this, so the copper chloride is going to run out first. So that tells me that's my limiting reactant. The copper chloride is limiting, it's going to run out. Now, how is this going to change? Well, again, you've got a 2-to-3 ratio of this, so this isn't going to go down by 0.005, it's going to go down by 0.0033 mole. It's 0.00333 because it's 2/3 of the copper chloride. So here we're using up 2/3 of the sodium phosphate. So now I also know what is in excess when I subtract these two things. Okay, I come over here to the copper phosphate. This is limiting. My copper chloride is limiting. But it's a 3-to-1 ratio between the copper and the copper phosphate, and a 2-to-1 ratio between the sodium phosphate and the copper phosphate. So what is this going to? Because it's a 3-to-1 ratio between the copper chloride and the copper phosphate, this is going to go down by, or go up, sorry, it's going to create, but it's going to go up by 1/3 of the amount, which is 0.00167. So 1/3 of 0.005 is this amount. So now I know how much of that I created. So now if I have to figure out how many grams of my precipitate, I now know, totally separate thing, I now know how many moles of my precipitate I'm going to create, 0.00167 moles, and now all I have to do is just convert that into grams. So I need the molar mass of copper phosphate, 380.5 grams over 1 mole equals, sorry, running out of room, so I'm going to stick my answer down here, 5 grams of copper 3 phosphate. Oops. And my handwriting is getting really messy. There you go. BCA tables.